Greetings everyone, Patrick here with Earth Patriot LLC. Earth Patriot is a platform for those who have the yearning to learn, grow, and be empowered by embracing sustainable solutions and practices in their daily lives. Today, I'm really excited because we're going to focus on the mechanical and electrical systems of a net zero energy home. When we think of a sustainable home, we must imagine a home that will provide shelter, resources, and longevity. A home that provides comfort, good indoor air quality, and a healthy environment. We want our home and our building to work for us, to be self-sustaining, to create the energy and resources required to sustain the needs of the occupants and the systems within the building. The mechanical and electrical systems we are going to review in this video were installed in a net zero energy home mentioned in previous video. Hit the link at the end of this video to see that video. The systems complement the home's design, and the home design complements the mechanical electrical systems. Fit for purpose. The systems complement each other, providing a synergy that leverages reliability, resiliency, and redundancy. So let's jump in. So the mechanical system plays a major role in the operation and performance of a net zero high performance home. The design process starts with the heating, cooling load calculation, sometimes called a building model. This is a calculation based on a multitude of factors such as the building orientation, building materials and fenestration such as windows and doors, insulation, the R value of materials, the U value of the windows, and all the materials have a value, right? So you have to understand what the value of all the building materials are within the building. You have to look at the dimension of rooms and the number of floors. So taking all that data, today we use software to run the calculations to provide the heating and cooling load based on outside design conditions for the location of the building. So I am simplifying the process, but without an accurate load calculation, you're unable to properly size the HVAC equipment. So, and most municipalities, building inspection departments will require a copy of your load calculation in order for you to pull the building mechanical permit. And there is several load calculation software available on the market. It's strongly recommended that you refer to the ACCA, Air Conditioning Contractors of America, for an approved software list. And the link below is listed here. All right, so once the heat load calculation is completed, obviously you would want the most efficient HVAC system to achieve net zero slash high performance home. Today's HVAC industry has many offerings. The choice of the type of system would really depend on the application, where the equipment, ductwork will be located within the building envelope and outside. We want the HVAC system and ductwork to be in what we call a conditioned or semi-conditioned space to avoid thermal losses or thermal gains from the ambient temperature. Basically, we try to avoid having equipment in a hot attic or in a cold crawl space. Those locations are really detrimental to the efficiency of equipment. Think of having HVAC equipment and ductwork in a hot attic in the summertime. The heat in an attic can be up to 140 degrees and it emanates into the ductwork. That's called a thermal gain. Opposite to that, if you have your equipment in a crawl space and you're in a cold climate, you would have high humidity and sometimes relatively cold ambient temperatures that would extract heat loss from the ductwork and equipment as well. which will lower the efficiency of the system. So you have thermal losses. So we really prefer to have our HVAC equipment in a conditioned or semi-conditioned location within the building envelope. Ductless, we have equipment choices are heat pumps, both air source and water source, split systems, package systems, ductless systems, and what's recently on the industry is what we call variable refrigerant systems that are also highly efficient. Notice I did not mention natural or propane gas furnaces. Today's sustainable home is not going to be utilizing gas appliances because of the move towards electrification and decarbonization. The home I mentioned in this video uses a water source heat pump, also called a geothermal heat pump. There are many benefits to using a water source heat pump. They're highly efficient. They have what's called a COP, coefficient of performance, of 4.0, meaning for every unit of energy you put into it, you get 4 units of energy out of it. The equipment also resides inside the building and is relatively quiet. Plus, you can add what's called a superheat coil to extract heat from the compressor for your domestic hot water. It preheats your domestic hot water when the unit is running. The cost of a water source heat pump installation is a higher cost, of course, initial cost. But if you bury the cost of the installation in your mortgage, you get what's called a net positive value. Typically, the savings provided by a geothermal system exceeds the monthly payment, extra cost of the monthly payment of the loan. You get what's called a net positive, and you enjoy net positive savings, and you enjoy all the benefits of a geothermal system without the upfront cost. There is also, in most states, I guess nationally right now, and if your state recognizes geothermal as a renewable energy, there is also a 30% tax credit available. Okay. I often mention the phrase fit for purpose. You want to design your system to serve more than one purpose. For an example would be if you install a heat pump that has a 2-speed compressor or is able to turn down the fan speed, the CFM output, cubic feet per minute, fan output, air speed. This could be utilized to provide dehumidification without overcooling the space. Another example would be utilizing your ductwork to optimize indoor air quality, providing or introducing outside air for ventilation, dilution of pollutants, and also having a high efficient filtration system, a high efficient filter within your duct system to provide a healthy indoor environment. So my choice of HVAC equipment, as you probably understand or see, is installing water source, or what we call geothermal systems. So a geothermal system pictured here serves multiple purposes. We have pictured on the left here a geothermal system, 2 located next side by side on the top, with thermal storage tanks located underneath it. This is critical in the design, again, fit for purpose. So what we recommend when we design homes is we have a location where we can install this type of equipment. It may be an isolated room, but you have to have the appropriate square footage to accommodate this equipment. Long gone are you can install equipment in a closet. Again, we spoke about not having your equipment in an unconditioned space, but a space that could be located, primarily centrally located within the building, but also have the ability to properly service the equipment, having the space to service the equipment. So what we have on the left is pictured 2 geothermal systems. The geothermal system on the left is a water-to-water heat pump that heats the water stored in both thermal storage tanks via heat exchangers. These heat exchangers are located in the tanks themselves. The heat pump on the right is a water-to-air split system. The compressor and the coax coil are located in the equipment. What a coax coil is a water to refrigerant coil. It's kind of like a spiral coil where you have the refrigerant coil inside a water coil, right? It's called a coax coil. So the refrigerant from the compressor is either heating the water in the coax coil, it's either adding heat to the coil, to the water in the coax coil, or removing heat from the coax coil, depending if we're in heating or cooling, whether the climate, if whether a heating, cooling mode of operation. All right, so the air handler for that split system is located on the second floor in conditioned space, actually in the loft, which is another mechanical room. So the air handler also serves the heating and cooling for both the first and second floor via ductwork. Primarily, we use spiral ductwork, and we'll talk about that in future slides. So the heat pump sits on top of two water storage tanks. The tank on the left is a 120-gallon tank, storage tank, used for thermal storage for the radiant floor heating, serving both first and second floor. The tank on the right is an 80-gallon storage tank utilized for domestic hot water purposes. We will discuss the storage tanks in the next slide. Both geothermal systems share the same ground loop. So let's talk about geothermal. Geothermal ground loops can be configured in two ways: vertical and horizontal. The ground loop piping that is utilized is called HDPE, high density polyethylene pipe. It has a 50-year warranty, but will outlast our lifetime once it's in the ground. It's very durable. It doesn't move around. It's just there. And the purpose of the piping is we circulate water in most cases where we don't have ground freezing below. We don't have excessive ground freezing. We just use water as your heat transfer medium. In locations in the northern climate, you might add a antifreeze inhibitor onto the ground loop to prevent freezing. But in other states that do not have a high freeze, ground freeze, we utilize just water. And that's preferred because of the high heat transfer of just using water. So the fittings we use are also called HDPE, high density polyethylene. Typically, when we install it, we fuse the piping and fittings together. We utilize what's called socket fusion, or we can use butt fusion. Butt fusion is the same method that are utilized by the gas industry when they install gas piping. Basically, they use the same type of equipment to install the gas piping. So with vertical installations, it does require a driller, and they use the same methods as used if they were drilling a water well. The depth of the borehole varies depending on the geographic location. This location, it really depends on the ground, the type of ground, what they're drilling in, and that will determine, basically a HVAC contractor who specializes in geothermal will know the area and identify the depth that is required per ton. Typically, in my area, I would go 175 feet bore depth per ton. And when I say tonnage, it refers to the HVAC size. And this will be extracted from the heat load calculation that we spoke about on the second slide. So you have 12,000 BTUs per ton. A typical home may have 3 or 4 tons. So I require a 3 or 4 boreholes per installation. In commercial applications, we will use what's called a TC, thermal conductivity test. It is performed to identify the heat transfer rate of the borehole. Typically, this is done on commercial applications because of how critical it is to understand the thermal conductivity of the ground, because we don't want to put too many boreholes or not enough boreholes into the ground for a commercial application. On residential applications, you will find, again, typically 2 or 3 or 4 boreholes. So after the driller drills the boreholes, and the HVAC contractor inserts the HDPE piping into the boreholes, we utilize what's called a thermal enhanced grout. We fill the borehole up with grout, and this enhances the thermal conductivity of the piping. So we want to make sure we have a surface area and we have conduction, right? This provides conduction from the ground into the actual piping. The piping has a U-bend pictured on middle picture below at the end of the piping. So you just have water. This is a closed loop system. You have water going down to the very end of the bore and coming back up. Typically, we use 1-inch piping for vertical loops. The vertical loops are then connected, tied back into what we call supply and return headers. Usually, we use a 1 1¼ inch headers. Where would we go from the ground loops? We will run from the ground loops, from the headers into the house and connect to a flow center. The flow center is what you see on the left picture. Pictured there is a flow center with 2 circulators. Above the flow center is 2 pressure gauges and 2 temperature gauges. And from that location, we would run high flexible pressure lines, water hose run to the from this flow center to the heat pumps. I will note that it's very important that you have both pressure and temperature gauges so you can observe what's happening within the ground loop. This helps with also the troubleshooting of your ground loop and making sure that you could properly identify and diagnose any issues that come up with the ground loop. It makes troubleshooting maintenance a lot easier. So pictured in the middle on the top is what we call a flow center. Excuse me, not a flow center. It's called a purge cart. The purge cart is utilized when we do an installation. We have to purge the ground loop, whether it's horizontal or vertical. So it's actually a jet pump, jacuzzi jet pump, that we utilize to provide a high pressure flow through the ground loop. And what we're trying to achieve is reduce or remove any air within the system, even small micro bubbles, right? Because those small micro bubbles will aggregate and turn into a larger airspace, which may block the flow of the water. So we want to remove all air within the system. And so we run this flow center for, I would say, 1 to 1.5 days, making sure we get all the micro bubbles and all the air out of the system. And then we add a microbe inhibitor into the ground loop just to reduce any growth from microbes. So the picture below that is your HDE piping with the U-bend at the very end of it that will sit at the very end of the very bottom of the borehole. Pictured on the top right is a typical example pictured of a vertical ground loop, vertical boreholes for a typical home. Pictured below that is your horizontal trenching. And we prefer to do horizontal trenching because it's less expensive by utilizing that method. And I typically go 150 feet trench, 150 feet long, 6 to 7 feet deep, 3 to 4 feet wide. And I put 3 slinkies. What you see is a slinky. It's a type of tubing. So we put tubing on top of tubing in a circle pattern. And I would utilize that trench to install 3 slinkies, 1 on the bottom of the trench and 1 on each side of the trench. So approximately 2,700 feet per trench. And that would give me approximately 1.5 tons of capacity. And pictured below that is your typical HDPE piping. It's certified for geothermal piping. So you want to make sure it has that designation of HDPE piping for geothermal purposes. All right, I get on my soapbox and talk about ductwork and the ductwork design because the duct system has a major impact on the efficiency of your HVAC equipment. If not properly designed and or installed, it can knock up to 40% off the efficiency of your system. So while you purchase a high efficient HVAC system, it's only as good as the ductwork that's installed, attached to it. So it's extremely important that you properly design your ductwork and making sure that's installed and located in an area that's not going to be inhibited by high temperatures or low temperatures. So again, we want your ductwork and equipment preferably in a conditioned or semi-conditioned location within the building envelope. The duct design and type of duct used will have a huge impact on the efficiency of the HVAC equipment. Understand the air handler is designed to deliver an X number of CFM, cubic feet per minute, at a specific available static pressure. This is data that could be taken from the equipment manufacturer's specifications that comes with the equipment. It will give you the CFM availability at a specific static design. So the static pressure of a system is measured by the type of duct, the length and size of both the supply and return ducts. So by using what we call a ductulator, I know it's a strange sound, right? Strange word. The ductulator, the static pressure can be determined. The higher the system static pressure, the harder the fan must work to provide the airflow to satisfy the building load. More work means more energy and higher operating cost. So the goal of a good duct design is to keep the resistance to airflow to a minimum. We want to avoid a high static design. So let's talk about ducts. The primary duct used in residential today is flex duct. You've all seen the flex duct. Basically, because it's easy to install, reduces the installation time, and it's less expensive than any other duct materials to install. Unfortunately, flex duct has a high resistance to airflow. Flex duct has a helix coil of wire wrapped with a plastic liner and insulation. The air has to overcome the helix coil. It's equivalent to driving down a bumpy road. There's a resistance to airflow, a high static resistance. To compound this issue, the use of long flex runs creates airflow imbalance from room to room. It's difficult to air balance. You've all probably experienced rooms in your home where there's not enough airflow to properly heat and cool the room. And that's probably because you have a long flex run from where the equipment's located to the room air registers. We all experienced that. So, and you know, it exposes a room to being too hot or too cold, right? Lack of conditioned airflow. So to minimize static pressure and to optimize airflow, you want to use duct material that provides what we call a laminar surface, a smooth surface for smoother airflow. So primarily the best ductwork to use is called metal duct. You know, you all see metal ductwork. The ductwork is better. It's a better choice. And the ductwork comes in many configurations, either square, rectangular, or round metal duct. I prefer round ducts as they provide less turbulence. So, and turbulence could also cause resistance to airflow. Another key to proper duct installation is to oversize the duct, to increase the ductwork to the next size up to help reduce the static pressure. So there is a key on the return side of the air handler. This is a real key on installation on the return side of the air handler, is to have oversized ductwork. In most cases, we use high efficient air filters that have a high static resistance to static pressure. So by having a oversized return duct, it helps with the lowering the duct static to help with the high static resistance that you see in high performance, high duct filtration filters. So by combining a duct system made up of flex and high efficient filter, you basically reduce the system efficiency up to 30%. That's costing you money to operate and reducing the overall comfort of indoor air quality. To sum it up, you want fit for purpose. You want to design a duct system that will complement the operation of the system by reducing duct pressure and increasing efficiency and reducing operating costs while providing superior comfort and good indoor air quality. The home uses both primary and secondary air infiltration. This is what I recommend. In the home that I design, I would use a pleated pre-filter that's located in the living space, and also use a MERV, a 4-inch MERV, which is MERV being minimum efficient rating value of a MERV 12. This filter will be located at the air handler. So we actually have two filters, a pre-filter and the main filter. And the pre-filter would have what we call seasonal replacement. So you would replace the pre-filter every season with a heating and cooling season. Replace the pre-filter. And the 4-inch filter, with replacement of the pre-filter, a 4-inch high efficient filter may last up to 4 years, depending on the indoor environment, how dusty the indoor environment would be. So the high efficient filter does have a higher cost, but by replacing the pre-filter as often as required, you could reduce the need to replace the high efficient filter. I would say, within every 4 years, if you replace the pre-filter as needed. So what's pictured here on the top left is the flex duct. Now understand, when I say flex duct, there is a need for flex duct. When I design my systems, I design all metal duct work on my main trunks, and my branches, which branch out from the main trunks, I would also use metal duct work. But the transition from the metal duct work to your register, I would use flex duct and try to keep it to a minimum of 7 feet of flex duct. That does two things. It provides ease of installation of the transition from the metal duct to your register. It also, the flex duct acts as a sound attenuator, which means it reduces the sound velocity noise of your ductwork. So I'm not against using flex ductwork. It has a purpose, but should be used in only locations that really are necessary. The picture to the right of the flex duct is hard duct, right? You have square duct, you have oval duct, and like I said, you have round duct, which I prefer to utilize. It's the round duct. But in either case, you would utilize a ductulator. Picture to the extreme right above me. That's a ductulator, and that is utilized to identify the static pressure, the resistance to airflow, depending on the duct material and the length of duct. On the bottom left, we have a duct system that illustrates the static pressure drop as you install the ductwork and the fittings within the ductwork, and the pressure drop of the duct and the duct fittings. And that is utilized when you have that duct system. You design the duct system. It gives you the ability to design and understand the total duct system drop on the return and the supply. And that helps with designing a duct system. There's more to it, but I'm just telling you the top specifications, or the correlation between duct and static pressure, which is extremely important. So it's important that your HVAC contractor understands that, and it's not just throwing in flexible duct work. So please speak to me if you have any questions or comments, and we can review your duct design, and I can help you design a duct system. All right, so let's talk about hydronics. Hydronics being you're moving fluid, in this case water. Water is the heat transfer medium through piping. We use copper piping, basically, other types of piping, and also PEX tubing, right, for the radiant heating. So we're either removing or adding heat to different locations within the building and equipment. So pictured on the left, we have two storage tanks. The one on the left is used for radiant heating, radiant floor heating, and the other on the right is used for domestic hot water. They both have two internal heat exchangers. So we use solar thermal hot water and water-to-water heat pumps to heat the water in the thermal storage tanks. The hot water for the two tanks can be supplied by three sources. The first source is the solar thermal panels. We have 3 4x8 solar thermal panels on the roof. In this case, we use what's called a closed loop system. The solar thermal loop supplies hot water when the sun is out to the two internal heat exchangers in each of the two storage tanks. We utilize circulators. Circulators will circulate the water. In this case, the solar thermal hot water will prioritize the hot water to the domestic hot water tank to a temperature of 160 degrees. Then, through a 3-way diverting valve, the remaining hot water from the solar thermal solar thermal hot water panels will be diverted to the radiant storage tanks. So we prioritize the domestic hot water heat first for the domestic hot water, then we move that through a diverting valve, the heat to the storage tank for the radiant heating. This is done automatically through temperature sensors on the solar panels as well as in the storage tanks. The second means of heating the water in the storage tanks is we utilize the water-to-water geothermal heat pump. The heat pump will come on when there is no solar heating available, like on the cloudy days or at night. The hot water created by the heat pump will circulate through a different heat exchanger in the thermal storage tank. So again, each tank has two heat exchangers, one for the solar thermal hot water and one for the water-to-water heat pump. So the third method of heating the water in the thermal storage tank will be an electric element in the tank. We all have electric heating elements if you have electric hot water. So these electric elements act as redundancy to both the solar thermal and the water-to-water heat pump. They are also employed when there's an excess of PV photovoltaic power available because it's free power, right? Free energy, right? So if I have, or there is an opportunity I see when I program these systems for operation, if I see there's an excess amount of photovoltaic power that's not being utilized for any other resources in the house, appliances in the house, and there's available sunshine, I would divert that energy into creating hot water. It's free heat, free energy, right? Both the first and second floors are concrete in this application in the home that we see in this design. So radiant heating is an economical, very comfortable type of heating. If you've ever been in a home that has radiant heating, you will experience this as soon as you walk into a room that has radiant heating. It encompasses you. So the radiant, we have what's called PEX tubing embedded in the concrete, creating the PEX tubing is embedded in the concrete, right, creating a thermal mass. Once the heat slab, what we call a slab, heats up, it takes very little additional heat, BTUs, to maintain temperature. Other forms of radiant heating that you may see in the industry are available, are also called staple up application installation. Staple up, we install the tubing, we staple up the tubing, utilizing heat transfer place underneath the floor, underfloor installation, right? We use what's called heat transfer place to transfer the heat from the tubing to the subfloor. We also have what's called embedded tubing sandwich in the subfloor. So there's other means of installing radiant heating, but I believe the most efficient way to install radiant heating, the most efficient way is with concrete. Being concrete is a thermal mass, and it holds the heat longer and takes very little BTUs to keep that temperature up. So let's talk about radiant heating, how radiant heating works. It works through radiant energy waves emitted by the floor. The radiant energy heats all the surfaces in the rooms, the walls, ceilings, all the objects in the room. So the room heats up to what we call a mean temperature. This creates a very comfortable environment. And when your feet are warm, your body is warm. It also provides improved blood circulation for the elderly. So it's a very comfortable, economical, healthy way to heat. In most cases, it's the primary source of heat, backed up by your typical HVAC heating and cooling that provides heating and cooling for your ductwork. So typically you would see both radiant heating and an HVAC system in a home. But because of the many ways to heat that water, it's very economical and is very comfortable to have radiant heating. Another thing is when you have high ceilings, it really doesn't matter how high your ceiling is. The radiant heat is going to heat all the surfaces in the room and provide an equal amount of heating. All the temperatures in the room provide a comfortable heat at the same temperature. Let me give you an example. When you're in a supermarket, a food store, I don't know if they call it supermarkets anymore, a food store, and you walk down the frozen food aisle, right? You can feel uncomfortable, right? So what's happening is your body is losing heat because the cold aisle is extracting heat at a fast rate. So you feel uncomfortable, right? But understand the temperature may be 70 degrees. And you go in the aisle next to it, it's called the cereal aisle, and the temperature again is 70 degrees. You'll feel comfortable because in the frozen food aisle, you have surfaces that are cold. They extract heat from your body, which makes you uncomfortable. So the theory behind radiant heating is all the surfaces, even the glass, all the surfaces are at the same temperature, the same mean temperature, which lowers the ability of cold surfaces to remove heat from your body. So you don't feel drafts, you don't feel cold near like windows or cold surfaces like the exterior walls. So it's very comfortable. It's a very extremely comfortable heat. So there are numerous reasons for your use of radiant heating. So again, it's a primary source of heat in most applications, backed up by your HV system. Your HV system be a secondary source of heating. So picture below, we have on the left, we have the geothermal heat pumps. The one on the left is your water source heat pump, providing heat to the thermal storage tanks below it. Picture top right is the water source heat pump. Notice again, we have temperature and pressure gauges, again, to do any diagnostic on the heat pump. To understand how the heat pump is operating, we balance the water flow through the heat pump to optimize the temperature rise within the coax coil within the heat pump. Picture below that is the three 4x8 solar thermal hot water panels on a roof, and the roof is a standing seam roof. Utilizing a standing seam roof helps the installation of panels, both PV panels and the solar thermal panels, basically acting as the point of contact for the panels. So again, fit for purpose, utilizing a standing seam roof is the best roof covering that you could have. It acts as a tool, right, to provide the installation of your panels. Fit for purpose. All right, let's talk about an ERV, an energy recovery ventilator. Indoor air quality is very important in the high-performance home that was designed as a tight building to reduce air infiltration and exfiltration of air in and out of the building, the home. So the buildup of pollutants, VOCs, volatile organic compounds, which is off-gassing from materials in the home, is a concern. Outside air is introduced into a home via an ERV, an energy recovery ventilator, to reduce the pollutants to a safe level, achieving safer indoor air quality. The ERV brings in outside air while removing stale, contaminated inside air. The ERV has two fans to move the air, and there's also dampers to help balance the airflow within the ERV. Now listen, the two air paths move across what we call the heat exchanger. The heat exchanger transfers air and either adds or removes humidity, but the two air paths do not cross-contaminate each other. This is very important. They go across the heat exchanger, but the air paths do not cross-contaminate each other. They're separate air paths. So basically, in the winter, in the cooler months, cooler outside air crosses over the heat exchanger and is preheated by the inside air leaving the home. In the summertime, warm or hot outside air is pre-cooled and conditioned, meaning humidity is removed, by the lower humidity cool air that is leaving the home. So it's preconditioning the hot, humid air as it comes into the building. So basically the ERV preconditions the incoming air by both removing or adding both temperature and humidity to the incoming air into the house. So these homes, the home ERVs, typically for a home, are rated by CFM, and they are usually rated by 100 or 200 CFM. Now the ductwork for these systems can be installed in two ways. First, the ductwork can be ducted into the existing HVAC ductwork, utilizing the HVAC duct for distribution throughout the home. This may require that the HVAC air handler be turned on when the ERV is operating to move the air throughout the home. The second method is having a separately duct system for the ERV. This is the preferred method. So when return air from the home is usually taken from areas that have high contaminants like kitchens and other possible bathrooms as well. The supply air is usually ducted to the supply air from the ERV is usually ducted to the main living areas. Again, it's essential that the ducts are of metal material and the lengths of ducts is kept to a minimum. The ERVs have small fans that cannot overcome high static ductwork. Placement, again, of the ERV is critical for this reason. So you want to place the ERV, again, in a semi-conditioned location, preferably in the central location of the home or where the air is going to be removed and ducted to the outside. So again, location is very critical in the design of an ERV. So two takeaways is the ERV needs to be located centrally in the building, and the use of hard duct to minimize high resistance is also critical as well for the distribution of airflow. And keep the ducts to a minimum. Again, they have small fans and they cannot overcome high static resistance. All right, we're going to talk about whole house dehumidification. In the US, the states that experience high humidity in the summer months, it's recommended that supplementary dehumidification equipment be installed to reduce what we call the latent high humidity loads in the house. It's true, the conventional HVAC unit will cool and remove humidity from the air in the house, but that may not be enough, and we don't want to overcool the house just to keep the humidity to a comfortable level. Utilizing a standalone dehumidifier will keep humidity in the house at a comfortable level. The whole house dehumidification unit would require ductwork, just like the ERV previously mentioned. The ductwork for the whole house dehumidifier can be ducted into an existing HVAC system ductwork or can be separately ductworked. Again, the ductwork, as I mentioned before, is the key to all systems. So we want to keep the ductwork and fittings, preferably metal material, and possibly in keeping the ducts to a minimum. The preferred setting for a dehumidification, preferred RH setting is 50%. Remember, high humidity in the house could lead to mold growth and very uncomfortable situations. So 50% or lower is a setting. Again, we want 50%. If you start lowering your humidity sensor lower than that, you got to look at energy costs. So we want to keep it at a comfortable level, comfortable RH level, relative humidity level. The lower the setting, the more energy to be consumed. The whole house dehumidification unit also has filters in the unit. Installing a high efficient unit or pre-filter is optional, but remember that these units have a small fan again and cannot overcome a high static ductwork or filter. Again, the location is key for these dehumidification units. We like to have the unit located in the conditioned or semi-conditioned space or mechanical room. All right, so we're going to move over to electrical. So pictured here is a 12 kW pictured on the wall above the electrical trough. We see a 12 kW solar inverter manufactured by Solark, SOL-ARK. And to the left of that, sitting on the floor, is a lithium iron phosphate battery manufactured by Fortress. It's an 18.5 kW battery, kilowatt battery. It's a 370 amp hour battery. This battery has a BMS building management system that monitors the charging and discharging of the battery, optimizing the performance and longevity of the battery. Together, the battery and the Solark inverter, together, this system provides 2/3 of the home power consumption. The technology for the solar PV with battery backup has come a long way, and so have the National Electric Codes. If I were to install the same system today, the equipment would have to be placed in a dedicated room within the building or be placed outside the house, as the new electrical and fire codes dictate stringent codes that make it almost impossible to install without providing a dedicated room for the battery because of the fire ratings. The fire ratings for a battery located in a occupied space is pretty stringent. Therefore, I see homes having to provide an attached or detached room to accommodate the solar inverter and batteries. So something to think about when designing a home. But overall, if you're going to design a net zero home, it's essential that of course you're going to have a PV photovoltaic system with battery backup to provide power, to provide also reliability for electricity, resiliency, and redundancy. So it's very essential that you have that. But again, you have to make sure that you're properly designing this system, and you have to adhere to the recent code changes in the NEC National Electric Code and the fire codes, NFPA 70 fire codes. So making sure that you work with an installer that understands these codes in order to provide a safe, efficient system, and also passes the fire and electrical inspection. So yeah. To summarize what we spoke about, Designing a net zero home requires some forward thinking. Utilizing high efficient equipment and optimizing the installation and operation of the systems is very important to keep the energy use down and the comfort and indoor air quality at its maximum. The systems should have synergy, working together to complement the operation of the systems. This, in conjunction with high-performance design of the house, will provide a superior, cost-effective, low-maintenance home that will last generations. I hope you enjoyed this video, and if you are interested in designing, building, or want more information on high-performance building or other topics we spoke about, please reach out to me. I am very interested in designing and building more net zero homes, either one at a time or as a whole community. My future videos will cover more sustainable building and living topics. So be sure to hit the like, share, and subscribe button to stay informed on new technologies and designs related to sustainable buildings and live-ins. We'll see you in the next video. Until then, stay Earth Patriot strong, people. Thank you.